Startet heute Abend um 20 Uhr. Ihr könnt ihn bis zum 17.12. nächste Woche um 18 Uhr machen. Our lecture today will be in English. I'm very excited to introduce to you Maya Ben-Yami. She is a research associate for Niklas Börs at the Technical University of Munich and a doctoral researcher at Potsdam-Institut for climate impact research. Today, she will tell us about tipping points and the Atlantic Meridional Overturning circulation. Welcome, Maya.
Thank you. Should I share my screen? Yes. Okay. Here we are. Let me know if you don't see anything correctly. So yeah, thank you for the introduction. Hello, everyone. I'm Maya, and as it was said, I'm going to talk to you today about the Atlantic Meridional Overturning circulation, which we always shorten into the abbreviation AMOC. So from now on, I'm going to be calling it the AMOC. And if you're interested in climate science but aren't like a physicist or a scientist, you may think that like you haven't heard about this part of the climate before. But maybe you've seen a headline like this that said something about the Gulf Stream collapsing, maybe quite soon, or something about like an ocean current that's going to cause like a new ice age and turning the UK as cold as Scandinavia. And actually, all of these headlines are about the AMOC. And I hope that by the end of this presentation, I can sort of give you enough knowledge and context to really understand articles like this, because the AMOC can show up quite a lot in the media, and it's always good to have a deeper understanding. Um, so the way I'm going to go through the presentation today is first, we're going to basically talk about what the AMOC is, then sort of transition to why do we care about the AMOC? Why is this a system that is important for the climate in general? And then also consider, should we be worried about the AMOC, in the context of climate change? That's also where tipping points are going to come up. And then I also want to give you just a few examples, like a sample of like current research to give you an idea of like what are the boundaries that we're currently pushing in our knowledge of the AMOC. And then like also touch upon the AMOC in the media, like I was talking about in those articles, and sort of understanding the context. And then, of course, I'll conclude and give you some take-home messages at the end. Okay. And I don't know if it was said before, but I'm going to also do a break in the middle for like 5 minutes. So yeah. So what is the AMOC? The basic definition that you probably see if you sort of read just an article or open the Wikipedia, you see an image like this, and it's defined as a current system in the Atlantic Ocean that basically takes heat and salt from the south to the north. And in this figure, these red lines that you see, these are warm surface waters, so warm surface currents on the sort of top of the ocean, traveling overall from the south to the north. Obviously, there are some these circular eddies, and there's like some gyres in the middle and stuff like that. But sort of the overall transport is these sort of warm currents going to the north. And then in the subpolar North Atlantic, so here in this sort of northern region, I hope you can see my cursor. There's sinking happening, and then you have this blue line, which is a deep, dense, cold water current, right? So, and that is coming back downwards to the south. We actually call these deep waters if you ever see the abbreviation of DW. So this is sort of the overall view of the AMOC. But to sort of really understand what's going on here, I also want to give you a little primer in ocean sciences, because I've been told that this is a very general audience. Not everyone's going to be knowledgeable about the ocean. So to even understand what's going on with a big circulation like this, you first have to know that the ocean is the same as sort of the climate, weather systems, where there are a lot of scales. Um, And so there's the sort of smaller scale, which is on 1 meter, 1 kilometer, 1 minute, 1 day. So this is small scale mixing. So these would be small waves, a bit of like mixing of the surface, some like waves driven by wind. And then when you go up to scales of like 10 kilometers, 100 kilometers, something a bit more like the weather, which is on this time scale of a month, you get these sort of like mesoscale eddies. So mesoscale is just the name for the sort of middle scale. And eddies are these sort of circular swirling motions that you see in this visualization. And you also, all the other sort of little things here, like filaments and vortices and spirals, these are all what sort of the weather of the ocean, these sort of middle scale. But the AMOC sits squarely in the sort of large scale dynamics. When you're talking about something on the scale of 10,000 kilometers and, on times that are like 100 years, 10,000 years, climate change is obviously on this scale, something that's happening to the ocean all over and on the scale of a long time. But also, if you've heard of the El Nino Southern Oscillation, sort of big phenomena happening in large scales. And in this presentation, because I'm talking about the AMOC, I'm mostly going to be talking about large scale dynamics, talking about sort of the whole of the Atlantic Ocean. But this large scale is built up from the smaller scales. So obviously, if you're sort of interested in what is happening in the ocean on the timescale of a month, then you would be looking at these sort of things. And if you're interested in tomorrow, you'll be looking at sort of small scale mixing. And all of the sort of smaller scales build up the large scale. So even though today we're going to be talking about the large scale, I do think it's always important to remember that these sort of smaller things are part of it and are sort of like building up to it. Okay. Um, Another thing that's sort of good to understand about the ocean when we're talking is that, okay, the AMOC is current system, movement of water in the ocean. But in general, what could move water in the ocean? This is the point where I sort of maybe ask people to give me suggestions. And usually, the immediate thing that people will think about is like wind. The wind is blowing over the surface and it's driving waves because it's there. It can also drive some internal motion, some upwelling. Then you have something like the tides, which everyone knows, where the moon's influence I mean, the tides go up and down, but it can also cause horizontal motion. Then, of course, there's sudden events like earthquakes and storms, which can sort of make like a sort of trigger for the waters moving around for currents. But the most important sort of driver I mean, the wind is important, but the second very important one are density differences. So you have different temperatures and different density, different salinities in different parts of the ocean. And that causes different densities. And then you have the denser areas moving towards the less dense. So that's a big driver of currents. And of course, I also have topology here because that can also influence currents. For example, if you have, a current coming like this, and then it has to go over like a little ridge or sort of, go from a wider path to a narrower path, that influences the speed and the type of the current. So still in sort of an overview of the ocean, we were talking about these density differences, and these are the most important for the AMOC. The wind is also important for the AMOC, but on the large scale, it's the density differences. And we can look at the temperature all over the ocean. So this is a map of the sea surface temperature in the global oceans, sort of an annual mean over many years. And you can see, as you would expect, also it's similar to surface temperatures where it's warmer around the equator and colder around the poles, obviously because of the sun and how much sort of solar irradiation regions can get. But you can see that there are differences. The equator isn't the same everywhere. And this is sort of because of different like sort of currents and heat transport and things like that. So you can already see some differences. But it's even more obvious when we look at salinity. So this is sea surface salinity in the ocean. Here, the lighter colors, so white is more salt and dark is what we would call fresh water. So you have salty water, and fresh water is not water without any salt. It's just water that's fresher than the water there. And you can see quite clearly that the Atlantic Ocean, which is over here, is much saltier than the Pacific. And the Mediterranean is obviously also very salty. And this is sort of influenced partly, so the things that influence salt is, for example, evaporation. So the water evaporating because of heat, it leaves the salt behind, or if it freezes, ice also sort of freezes out the salt. Or if you have ice melting, that's basically a freshwater source that brings more fresh water in. You have rivers bringing in fresh water, um, rain, precipitation bringing in fresh water. All of these influence how salty the ocean is in different places. And sort of these two things, the temperature and the salinity, combine into this map, which is the sea surface density. Obviously, for the sort of big movements in the ocean, we also would need to look at the density, deeper in the ocean. But this does give you a view, the density at the surface of the ocean. And if you look at the numbers here, these are very small changes. They're like smaller than 3%, but they are important because there are these changes, differences. And you can see the darker colors, these are denser areas. So you have these two areas, one in the Southern Ocean and this one here in the North Atlantic, which is an important area that is much denser. And this is sort of good to remember. Now I'm going to show you a short video. There's no need for sound, so I don't think that's going to be a problem, which basically demonstrates um, how sort of temperature differences can cause circulation in the ocean. What you have here is a tank of water, just normal water, and you have this ice cube over here, and here you have a lamp warming the water. So it's sort of a bit like the poles, the icy poles and the equator or something like that. And the experimenter put some blue dye in the water, and you can see how the icy water is colder, and so it's denser and it sinks down and it causes this sort of circulation because the water that is warmer rises up because it's sort of less dense. And you're basically getting this sort of circular circulation of like sinking down and then coming up and then coming around. Obviously, in the Atlantic Ocean, salt also plays a part, but this is just a demonstration of what can happen with a cold to warm contrast. So this sinking is very important. Yes. And like I said before, the sinking that if sort of you get a lot of water sinking down to the deep ocean, we call that deep water formation because basically you're taking surface waters and they become waters that are deep down, deep water. Very simple name. And these diagrams are basically showing the sort of deep water formation that is happening in the subpolar North Atlantic. Here you have it's the North America, Greenland, Iceland, Europe is over here in case you sort of needed some context. And you have sort of two major areas of sinking here. One in the Greenland, Iceland, Norwegian Sea over here. That's also what's shown on this sort of smaller image. I just added it so that you can see that there's a lot of complexity with sinking in multiple different regions and then them sort of coming around. And you also have this other sinking region. This area sort of south of Greenland is the subpolar gyre and specifically the Labrador Sea over here. And you also have sinking here. And you get these, the NADW stands for North Atlantic deep water because it's deep water that's coming from the North Atlantic. U and L stands for upper and lower because the water that forms in this sea is a bit denser and so it's a bit deeper. But this sort of sinking that is happening here, this is a very important driver of the AMOC, and it's a very important component of the AMOC. And we'll come back to this when we talk about climate change and how it affects the AMOC. Okay. So as I was saying before, here you again can see this map that I was showing in the pathways. And this is mostly how we'll be thinking of the AMOC today, as the sort of pathways of warm currents going to the north, sinking down, and then coming back. And obviously, though, there's a lot more complexity. The AMOC is a 3D circulation. Here you can see a map on the top, it's sort of currents, and then you can have this sort of slice where basically the red is the darker colors of reds are showing you where the circulation is stronger or weaker. Um, I'm not going to go into detail into this, but I have provided supplementary notes for the presentations in a PDF that you'll probably get. It has a lot more text, and this is sort of a section that I go a bit more into in those notes, in case you're interested in how we sort of plot and understand the circulation in depth. Okay, so why do we care about the AMOC? Um, yeah, sorry. Yeah, now that we understand what the AMOC is, why do we care about it? Why it's like an interesting system in the climate, but there's so many interesting things in the climate. Why is this something in particular that is worth studying? So I like to start talking about this by mentioning that the AMOC is special. So if you had a planet, you could imagine, some planet around another star, or just, like a sort of thought experiment of a planet that is all water. No sort of geography or anything to think about, but sort of same relationship to the sun. In that case, you wouldn't have an AMOC. You would have a circulation that sort of sinks at the poles and comes up at the equator, sort of like the video that I was showing you earlier. But on our planet, because of sort of the geometry we have, we do have an AMOC. There's no big mock. There's no like something going up to the north and sinking down over the whole sort of basin in the Pacific. What you can see here in this figure, it's maybe a bit confusing, but it's Antarctica here. You're sort of viewing the planet with Antarctica at the center, and you can see what is sort of called the conveyor belt. Sorry, the conveyor belt of ocean circulation, which is the AMOC is over here in the Atlantic with these warm currents going north, sinking, coming back cold. But you can see that in the Pacific, you just have this sort of upwelling going up in the equator and coming back, and there's no sort of like whole basin circulation. And the reason for that is sort of there's multiple reasons that lead to the AMOC. One of them is just the geometry, that you have sort of the Atlantic basin is smaller. You have this very sort of thin passage between South America and Antarctica, the Drake Passage. Another important reason for the existence of the AMOC is the fact that in our planet, we have this very unique Antarctic circumpolar current. So because there's nothing like sort of in the way around Antarctica, you get this like very important circular current around there, which can help the waters to sort of come up, right? They sink in the North Atlantic and then they upwell, they come up in the Southern Ocean. And also, I was showing you before on that salt map of the saltiness of the ocean, that the Atlantic is much saltier than the Pacific. And that's important because you need the salt for the water to be dense enough to sink. It's very important the Atlantic is salty enough for there to be this sinking, this deep water formation happening in the north. So we can't take the AMOC for granted. It's a special thing. And these figures here, so this slide is now when we consider what happens if we turn off the AMOC. That's sort of the easiest way to understand why the AMOC is important. What happens in a climate model if we just switch off the AMOC? So there's multiple things that happen. The most important that I'm going to focus on today is the fact that the AMOC transports so much heat. So here on the figure on the left, you can see that basically if you shut off the AMOC, all the sort of heat that is going to the north isn't there anymore. And you have this blue region, which is a widespread cooling over the whole of the North Atlantic, right? You can see it sort of goes up to like 7-8 degree difference. So in areas, it would be 7 degrees colder. This is obviously not like, this is just a model. So the numbers are not like anything, any prediction or anything like that, but it is indicative of the sort of big widespread cooling that would happen if the AMOC wasn't there suddenly or wasn't circulating anymore. Another really important one is precipitation, because the sort of regions that are the warmest or sort of the big band of sort of tropical rainfall that sort of goes around and sort of near the equator, it's sort of determined by also the temperature balance between the different hemispheres. And if you change the temperatures so much, you get this right-hand side figure, which is the difference in precipitation. If you turn off the AMOC, you get these sort of green regions, which you can see here, which is basically a lot more rain, and then the brown regions are less rain, right? And what we're basically seeing is that this sort of like band of rain all shifts to the south. So obviously there's also drying happening in the northern hemisphere, and there's also this tropical rain band which is shifting to the south. Other changes also include the fact that the AMOC, usually when it's sinking down in the north, it takes anthropogenic carbon with it and sort of stores it in the deep ocean. It stops doing that. Obviously, when currents change, the sea level also changes. There's regions in North America which would see sea level rise if the AMOC turns off. But I personally work on the effect that turning off the AMOC would have on the monsoons. So this is a figure from one of my papers where we sort of showed that if the AMOC turns off, if basically we turn down the strength of the AMOC from what it is now to zero, you basically, what you're seeing here in the red regions is a shorter wet season down here and a longer dry season in monsoon areas. So these are all very important sort of ecosystems on our planet, and all of them would see quite severe consequences because of these much longer dry seasons and shorter wet seasons. Okay, so I hope that I've really showed to you why the AMOC is important, and it could really affect temperature and precipitation and sea level and carbon uptake on our planet. But should we actually be worried? In the context of climate change, is like the AMOC something that we should be thinking of? And of course, I'm here because the answer is yes. But I, of course, want to explain to you why exactly that is. So if you remember, I was talking before about this sort of sinking that happens in the North Atlantic, the deep water formation, and the need for the water to be dense enough. This needs to be salty and cold water for it to sink. And what happens when you warm the planet is that, first of all, it gets warmer, of course, but you also get more rain in these regions, and you get melting ice. So, of course, there's big fears of like melting ice sheets from the Greenland ice sheet, but you also just have melting sea ice, all of which brings more fresh water into this region. And this fresh water is lighter. So, all of this region is becoming less dense. And that means that there's less deep water formation, less of that sort of like engine that is driving the AMOC, this formation of this deep water, which is part of the circulation. So that is why the AMOC weakens when we warm the planet. And that is definitely not a question, whether or not the AMOC is going to weaken. So what you can see here on the right is results from complex climate models, which if you haven't heard about sort of how we model the climate, one way that we model the climate in climate research, you can see sort of here on the bottom left, we have these sort of huge, very expensive, very sort of like complex models where you take the planet and you basically chop it up into lots of little boxes. And you sort of write equations for how these boxes interact, based on the laws of physics and other things. You parameterize things like clouds, and then you run a huge computer simulation to basically see what would happen in the future in the planet. And this is sort of how you get results like this on the right, which is coming from the report from the International Panel on Climate Change. Maybe you've heard of it if you're sort of interested in climate. It's just this sort of UN summary of sort of climate research. But the important thing is the line here, this black line and then the colored lines, this is just a representation of the strength of the AMOC, right? So up here is stronger, down here is weaker. And the different colors are different future scenarios, right? So the red one is sort of unchecked fossil fuel economy. And then the light blue one is we basically do everything we've promised to do, and we try really hard to mitigate and stop climate change. And you can see that in all scenarios, the AMOC is going to weaken up until 2100. You can already see that in sort of the lighter blue scenarios, it's starting to get stronger and maybe go back up. But in these other ones, it's going to weaken. There's obviously a huge spread. The sort of shading in the background is a spread between different models because you have dozens of these models to sort of look at. But yeah, the AMOC weakens when we project what will happen in the future because of climate change. And I'm also now going to show you a result from a recent preprint. I'm very cautious about showing preprints because obviously they haven't been through peer review. No one really has looked at this. Anyone can upload a preprint, but these are just simply model results. So I think they're probably going to be okay. Um, and basically, this is a recent preprint that shows that, again, all these lines are the strength of the AMOC. Now you have like each line is a different model, right? Like a different model from a different country that is like this. And you can see that sort of in these dark, all these sort of dark red or orange colors, the AMOC goes down to almost zero, basically what we would call a collapse, the AMOC turning off. And that happens after 2100. So the reason you don't see it here is because it stops at 2100. But if we continue the projections afterwards, by 2300, 2200, the AMOC, this is in high emission scenarios, but it is an important result. So is this the reason we're worried about the AMOC, that it might turn off because of climate change? Yes, that is one reason. But another reason that we're worried is because we think and the AMOC might be a tipping element. And so I want to do a quick aside about tipping points and what they are. And then we can come back to the AMOC. And because also tipping points are generally important in the climate. So one of the many definitions of a tipping point, this one is again from the International Panel on Climate Change, is that it's a critical threshold beyond which a system reorganizes, often abruptly and or irreversibly. That's a sort of complex mix of words. But the reason I sort of have this animation here of the Jenga tower is because this is what I like to use to illustrate a tipping point. What you're having here is a tower and you're slowly changing something. You're pulling out one block, one block, one block, slowly changing something. And then suddenly you pull out one block and just one more block, and then the whole tower falls down, right? Just one block had a huge effect. Pulling out one block made the whole tower fall down. And this is sort of what a tipping point does, where the point is sort of the location in time, the threshold after which, if you do like a little change, the whole system changes, reorganizes completely from a standing tower to a fallen tower. And the terminology here, just because people do tend to get confused, I've gotten confused as well, is that the tipping point is the threshold. So if you're thinking of the tower, the point is the number of blocks you have to pull out for it to collapse. And the system is the tipping element. If we're talking about the climate system, it's an element of the climate system. So the block of towers would be a tipping element. The tipping point is the number of blocks. And also for sort of the next slide, I want to introduce the concept of a stable state, which is basically the state of a system where, first of all, we're interested sort of in two things. We're interested in states where which have equilibrium, which means that, you know, if I just walk away from the tower, you know, I pull out a few blocks, I walk away from the tower doesn't change. That's an equilibrium state, right? If you leave it alone, nothing is changing because we're interested in states in the climate that, like, if we don't touch them, nothing happens. But we're also interested in stability, right? Because in the climate, you have warmer years, you have colder years, you have like weather happening, you know, not just sort of this big push that we're doing as humans, but also just like small perturbations all the time. So we're also interested in stability in states where if you sort of give it a little push, it won't fall down. In the sort of in the example metaphor of the Jenga tower, I like to think like blowing on the tower, you know, when the tower is sort of like at the beginning, you've only pulled out a few blocks, like at the start. If you sort of now give it a little nudge, it's not going to fall down. It's pretty stable. But as you pull out more and more blocks, it becomes more unstable, right? Because if you give it a little push, it's not going to come back. It's going to actually fall. That's not a stable state. Yeah, so we're interested in states that are both sort of, if you leave them alone, they stay like that. And also if you sort of give them a little push, they come back to it. That's a stable state of the system. And the reason that I've gone on about this is because I want to show you a mathematical example to give you an idea of sort of how tipping points work in the system. And don't worry, I'm not going to show any equations. If you're interested in the mathematics of it, um, I have more sort of explanations in the supplementary notes. But in this presentation, we're just going to be looking at this sort of like figure, these lines here, where basically what we're seeing is this is sort of like an example of a system, right? It's a system that I set up with a mathematical equation. It's an example of what might happen. And what you're seeing here is that from down to up, you have the state of the system. So this could be how tall the tower is, or how strong the AMOC is, how many trees there are in the Amazon rainforest, how tall the Greenland ice sheet is. And then sort of here in the bottom from left to right, you're changing something that we call the control parameter. So for the Jenga tower, that's the blocks that we're pulling out. That's how we're changing the system, controlling it. Obviously, for the whole climate system, that's the temperature. So we're changing the global temperature, and that's how we're controlling the system. For the Amazon rainforest, it would be, how much rain is happening, and you're changing it from like more rain to less rain, or colder to hotter, something like that. And these two lines here in this figure are basically one stable state and another stable state. So this is what's sort of special about the system, that it has multiple stable states, like for the tower in a way. So the way it looks for the tower is that one of the stable states is standing tower and the other stable state is fallen down tower. That's sort of how I like to think of it. And as you're changing the control parameter, which as I've said is the amount of blocks that you're pulling out, you're sort of going along slowly. You're pulling out blocks, but you're still staying in one stable state, right? You're still staying in the tower standing state. But then you get to a point where tower standing can't exist anymore. Basically, if you've pulled out this many blocks, there isn't a possibility for standing tower to exist anymore, and you fall down into fallen tower. Or, in the AMOC, you fall down into AMOC off. In the Amazon forest, you fall down into no trees anymore. Um, and that's because sort of this thing where in some locations, for some values of the control parameter, you could have two different stable states are possible. But in some others, you only have one stable state possible. So the red lines here are different values of the control parameter. And I think this animation really shows you what is happening. This is me actually running this model. So this is all like the equations to the mathematical model running. And what you see here is that as we change the control parameter really slowly, the system sort of goes along this one stable state. You can think of it as the AMOC getting weaker as we weaken, as we sort of warm the climate. And then you get to this point, which we call the bifurcation point, after which there's just no more of the stable state exists. And then you sort of fall down to the other stable state. And the reason I've explained all this is because I want you to understand this next thing, where if we now try to go back, right, we're now changing the control parameter backwards, basically just doing the same thing we did forwards, just doing it backwards, going from we went from left to right with the purple line, now we're going from right to left. But because of the way the system is set up, we aren't going back the same way. It's a different path backwards. A sort of scientific term for this is hysteresis, which maybe you've heard in some other lecture course. But the important thing is that imagine now that this diagram is the AMOC, and imagine that sort of in the middle of the control parameter, that's sort of where we started, pre-industrial temperatures. And we're warming, and then the AMOC collapses to a weak AMOC. But now, even if we try to cool down the temperatures, right? Even if we go back to the temperatures that we had before we even started interfering with the climate, 1850, before the Industrial Revolution or something like that. Even if we go back to those temperatures, the AMOC might not get stronger again because maybe we're here in the middle, right? So there is a scenario where sort of the collapse of the AMOC is what I like to call practically irreversible. Not really irreversible, but in terms of like what we're going to do, irreversible, because even if we basically turn back the time, like the warming sort of like dial, and go back to the temperatures we had in 1850, we might still not be able to get the AMOC back to being as strong as it was before. This is why people are worried about tipping points in general. Not just because you have this very abrupt change, which is obviously worrying, but also because of this irreversibility. And yeah, okay, sorry, I thought something else was coming. But I think this might be actually a good point to take a 5-minute break, because the next thing I'm going to talk about is why we think the AMOC is a tipping point, tipping element. Um, so yeah, I think right now it's 10 to 6, so maybe at 6:55 we can continue. Okay, so I can't actually see if everyone's back or yeah, but I said 6:55, so hopefully it's all worked out. Um yeah, so we stop here. I'll just go back a slide. Yeah, at this sort of like idea of what a tipping point is. So obviously I've been talking already assuming that the AMOC is a tipping point, talking about it sort of like as being in different locations and sort of tipping. But I also sort of want to explain to you why we think that it might be. We're not certain that the AMOC has a tipping point and is a tipping element. But there is a lot of evidence to support that. So I want to introduce you to this evidence. The first sort of like reason that we think the AMOC might have a tipping point is because you need like a sort of feedback for this sort of collapse, for the tipping to happen. You know, this sort of like sudden change. What is happening here is basically that the system is changing by itself. You just sort of like push it, and then there's something inside the system which sort of drives it to weaken without any external influence. Sort of that's why you push it a little and it tips over. And the AMOC has this sort of thing. A feedback we basically call somewhere something in which you have this circular motion, right? You sort of do a plus and then another thing turns and then it sort of come back. I hope you'll see that when I explain it, because the way it works is that if you get a weaker AMOC, um, then that means that because the AMOC is this sort of current system that is transporting heat and salt northwards, if you get a weaker AMOC, you get less salt in the North Atlantic because it's transporting less salt to the north. So you have less salt in the North Atlantic. And that means that the waters there are less dense, right? As we've talked about before, you really need these salty, cold, dense waters for them to sink in the North Atlantic. So because you have less salt, you have less sinking, less deep water formation, and that sort of leads to the AMOC to be even weaker, because this deep water formation is an important part of the AMOC, right? You need this deep water to go down for the circulation to work. So less deep water formation, even weaker AMOC, and then you sort of go around again, and you can go around and around and around and around until the AMOC is basically at zero, right? Or close to it, at a very sort of weak circulation. So this is what would be sort of driving the AMOC towards zero. Obviously, there's also sort of like different feedbacks which are stabilizing the AMOC. That's why it's not like, you know, one warmer year would be like tipping the AMOC over. But this sort of point down here where a system tips, that's where basically this sort of feedback overtakes everything else. So the AMOC has a feedback like this. Also, this is sort of in the 60s already, people started modeling the AMOC as sort of a few simple boxes. So what you see here is something that is called the Stommel model. I'm not going to explain it in detail. If you want more information, of course, just as usual, go to the supplementary notes. The only sort of thing I want to show you that if you sort of model the AMOC as a sort of equatorial box and a northern box, you know, like a warmer and a colder box, a little bit like that water tank, then, and you sort of write down all the equations and you sort of work it out, you get this sort of like bifurcation diagram like we saw before, with here's one stable state and another stable state, and here the AMOC could tip to a different circulation. And people have, you know, made a lot of simple models like this. You have models with 8 boxes or 4 boxes or something like that, trying to model the AMOC with different levels of complexity. And you usually have this sort of bifurcation diagram. So simple models definitely show that the AMOC could have this sort of like multiple stable states and a tipping point. We also have evidence from the past. So obviously, we've only been like observing the climate as us, humans in detail for the past few hundred years. But if we want to look into the really, really deep past, which is what you call like the paleoclimate, so climates of the faraway past, you use what we call proxy records, right? So you need to sort of like find something that tells you about the climate back then, because it changed in the climate. So that could be, I think a lot of kids learn about, counting the rings in trees to sort of learn about the temperature or something, or you can look at fossilized leaves and count how many sort of like pores they have or something. But the most reliable sort of um, history book that we have of climates of the faraway past are ice cores, which you can see here on the top right in this photo. Basically, you drill down really deep, somewhere like the Greenland ice sheet, and you get the sort of like long, thin ice core, and you look at the chemical content of the little bubbles of air that you find in this core. And basically, the deeper down you go, the older the air is. And this air, or like sort of the stuff that you find in the ice core, it can go back even 800,000 years. And basically, it can tell you a lot. So the sort of line that you see here, this black line, this is sort of something, it's the ratio of different oxygen isotopes, but that really doesn't matter for what we're talking about today. This is basically, as it says here, it's a temperature proxy. So this is an ice core from Greenland, and they sort of counted all these things in the bubbles, and then they made this time series that basically shows you the temperature in Greenland going back very strangely from the right to the left. This is today, and as you go to the left, it's older and older time, right? So here on the left is sort of a long time ago, and here on the right, it's today. And the sort of numbers are how long ago it was. So 80,000 years ago, 100,000 years ago. And the important thing to see here are all the numbers. All the numbers are sort of labeling something that we call danska Öskar events, shorter DO events. And the reason these are important, and I'm showing you them today, is because you can see quite clearly in some instances this sort of like really sharp line up. So on the scale of like this time series, this is extremely abrupt, right? This sort of like warming up. These are these events. And basically, when you sort of, sorry, when you look at the science of why these might happen, basically people think that they're caused by a combination of the AMOC and sea ice in the atmosphere, but that the AMOC plays a really important part by basically turning on. So it's not exactly the tipping point that we're worried about today, because it's sort of like a turning on instead of turning off, quote unquote. But you can see that these happen quite a lot, and it's basically evidence from the really far away past that you can have this sort of like abrupt transitions in the AMOC from on the scale of like just 1,000 years or something like that. Um, Okay. And that's a very sort of important and strong piece of evidence. Obviously, the problem with this piece of evidence is that these are very different temperature conditions to what we have today and what we will have in the future. So it sort of tells you that the AMOC can have an abrupt sort of tipping, but it doesn't tell you if it's going to have it in the future. For that, what we sort of use is again these complex climate models, as I've talked about before, where you use like a really expensive, huge computing cluster to sort of really model how every part of the Earth is sort of like going to change into the future. Or in this case, not in the future, but in a sort of like idealized experiment. So what you see here on the right is a figure in which basically what they've done is they've taken the planet, you can see here in the inset, this little planet, and they've poured fresh water. I mean, obviously added it mathematically in the model, but you can think of it as them basically just pouring a lot of fresh water into this area, right? Which is a bit like what would happen if the planet was warming. Obviously, in the future, with climate change, we would have a lot more happening, not just this freshwater increase, but this is sort of what would affect the AMOC, what I was talking about before, about the ice melting and things like that, and freshwater diluting the salinity here, and so it can't sink down. And so what they did in this experiment is that they really, really slowly over thousands of years changed the amount of fresh water that was coming in here and like increased it slowly, 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 slowly. And then at one level of increase at this point, this number here is the amount that they're sort of like pouring in the fresh water. At one level of this control parameter, F, the AMOC, so the black line here is the strength of the AMOC. And suddenly the black line tips to a different stable state. So that is a strong evidence of the AMOC in this particular model being able to do this, right? And there's evidence from other models as well, where you sort of do this sort of like forcing it with fresh water. It's something called hosing, right? Because it's like you're taking a big hose of water and pouring it into the ocean. Yeah, so there's also evidence from these complex climate models that the AMOC can tip in this way. But you might be thinking, oh, but Maya, you showed us before here that like in future projection, the AMOC suddenly weakens. Isn't this the same? The difference here is that we just, first of all, it's the speed. So this sort of line could just be the speed of climate change. But also what we're worried about in a tipping point, you always have to make the difference between just an abrupt transition and an actual sort of what they call here a catastrophic bifurcation, an actual tipping. Obviously, the definition of the tipping point changes from paper to paper, from scientist to scientist. Some people might call something like this on the left tipping, and some people might call only the thing on the right tipping. There's actually some sort of pushback also against the term tipping because it's a bit vague. But the important thing to note is that there is a way, like the figure here on the left, in which you can sort of have this abrupt transition down, but without irreversibility, right? Because in this sort of case on the left-hand side, you go down along this black line and it's very fast and scary. But if you sort of turn back the warming to where we were before, you just go up. So in this, if the AMOC is like this, it wouldn't be irreversible if we made it collapse. But here on the right, this is what we were seeing before, right? And this sort of like animation that I showed you, where if you collapse, going back isn't the same as going forward. So it has hysteresis. This is also what I say up here in the text. So it's sort of important to make the distinction when you see like a figure of the AMOC really fast getting weaker, of making a distinction between sort of whether or not it's irreversible. Just seeing it sort of like getting weak quite fast, that doesn't mean that it's irreversible, but obviously it is still a worry. So both of these cases are something that we need to be worried about, but irreversibility only happens if you have multiple stable states. Okay, I hope that wasn't too complicated and that at least a few of the messages got through. Now that we've basically been through why we should be worried about the AMOC, not just because it might quite suddenly weaken and it is going to weaken with climate change, but also that it might irreversibly weaken. I want to do what I said before and sort of give you a few examples of what we as researchers are doing about the AMOC, obviously with a little bias also to my own research, because so much is being done out there and it's all really cutting edge and important. So the sort of thing that I always like to mention is that we are observing the AMOC in a way that is like really innovative. But as you can see in the previous slides, the Atlantic Ocean is huge and the AMOC is a very complicated and very big current system. So you can imagine that like actually finding out what is happening in the Atlantic Ocean over the whole basin in circulation is very different. So the way that we do that is basically by putting in these measurement arrays. So here on the left, you're seeing like a slice of the Atlantic basin, where here's Europe, North Africa, Greenland, North America. So this is a slice across 26 north. And what you can see here is a representation of this array where you put these little red lines. These are sort of measuring the values in the ocean along both borders. And then you also measure sort of the Gulf Stream in the Florida Straits, because there's a sort of like a telephone wire here, and you do sort of a magnetic measurement over it. And using some sort of like mathematical assumptions and calculations, you can get the strength of the flow. But this is like a huge sort of like infrastructure setup and the technological setup, and it's only been done since the 2000s. So what you can see here on the right is what the situation we have today, where all these sort of lines across the Atlantic basin, these are different measurement arrays that we have in the Atlantic, and they're all sort of very good. But here I'm showing you sort of like the data from these measurement arrays. And you can see that the earliest one starts in 2000, and a lot of them are sort of quite short, starting in 2014. Obviously, there's a little bit more today because this stops in 2020, but we only have about 20 years of measurements at the most of the AMOC directly. So this has given us a lot of information. I mean, just by looking at it, you can see that the AMOC is different at different latitudes, sort of a lot about the AMOC, but it isn't enough to say if the AMOC is weakening or not. But obviously, yeah. So what people use usually are sort of fingerprints for the AMOC, something like using a sea surface temperature, like I was talking for proxies before, where you sort of use something else to tell you about the system. Um, I also want to talk about my research into AMOC stability loss, mine and my supervisors and a lot of other people. So if we also want to know not just about, what will the AMOC do in the future, but also, is the AMOC already getting closer to the tipping point? We can use what I was talking about before in stability, where if you're looking at this purple line, it might not be very clear, but you can sort of see that as it's getting closer to this point, the sort of wiggles around are getting larger. The statistics of this sort of time series is changing. If you're someone that sort of understands statistics, you can think of it in terms of the variance increasing, the autocorrelation increasing, the restoring rate increasing, but it's not really important for this presentation for you to sort of understand those terms. All you need to know is that as a system gets closer to tipping, the statistics of what's going on change. It's called critical slowing down. It's like you can think of this tower as it's getting closer to falling down, it wobbles around a lot more, right? It's a lot more vulnerable to wobbling. And so what we can do is we can use this sort of like fingerprint of the AMOC. It's not a direct observation, but it is a time series that we think is basically representing the AMOC, which you can see here on the left, like some sea surface temperature-based fingerprints. And we can calculate this statistical thing, and we can see that it's been going up in a significant way. Like the ensemble here is sort of like observational uncertainties. So this is like basically evidence that the AMOC has been losing stability, has been getting closer to a tipping point in the past sort of like 150 years, because we're looking here from 1850 to today. Now, this obviously is not sort of like not enough of a message for some people, right? Because like a lot of people say, yeah, but like what we actually want to know is when is the AMOC going to tip, not is it already losing stability? Obviously, it's good to know, but what about the future? Can we just, like take this line and extrapolate it into the future? And there's been some studies that have like tried to do this, try to sort of like use historical data like we're using in these figures and extrapolate it into the future and try to predict exactly when the AMOC is going to tip. But in a recent study, my colleagues and I have basically shown that these sort of methods of extrapolating into the future from like historical data, they're way too sensitive. So what you're seeing down here is just what happens. We sort of took a method from the paper by Ditlevsen and Ditlevsen, and we basically just applied this method to different data sets of sea surface temperature. So nothing is changing here except sort of a bit how we define the fingerprint and how we take the data set. So we're basically changing something very basic. Like, you go online, you Google sea surface temperature, which of the few options do you choose? And obviously they use different things in these data sets, but they're all equivalent. You can't say that one of them is better than the other. And if you use different ones, you get predictions for when is the AMOC going to tip that range from 2050 to 5,000, and even like it goes up to sort of 8,000 in this sort of line that goes off the screen. And if you're sort of trying to predict something, you're asking when is the AMOC going to tip? And the prediction is, oh, maybe in 20 years and maybe in 6,000 years. That isn't really useful, right? It's not like these methods aren't like is theoretically good. It's just that they're so sensitive because you're trying to predict something in the future, and our data about history is so uncertain that we can't just do this sort of extrapolation and predict when the AMOC is going to tip. What we can do is use the sort of model predictions that I showed you before. I'm not going to go all the way back there now, but we're never going to get like an exact time for like this is the year the AMOC is going to collapse. We might get like a sort of temperature range or something like that. We might get we're getting very close to it, sort of like this from these statistics, seeing that we're getting closer and closer, but we're not going to be able to sort of predict an exact year for AMOC tipping. So that is good to know when you see the AMOC in the media. And now I think the time is almost up, but we're really getting to the end now. Just coming back to how we started the lecture, in terms of sort of these headlines that I'm showing here. I mean, I can reveal to you now that I chose these headlines because I think all of them are a bit extreme. Obviously, there's also a lot of good articles written about the AMOC, so I'm not saying that in general, but I want to explain to you a bit why the AMOC is sort of like why I think these are maybe extreme, and sort of give you a few tips for when you're reading articles about the AMOC. And just as a joke, I wanted to sort of like show you a very fun moment I had as an AMOC researcher, where in a meme group that I've been in since high school, someone sent this meme where I think it was like a year and a half ago when the Barbie movie's coming out, where you have like a sort of like this Gulf Stream could collapse as early as 2025, sort of cat being sad about it. And I sort of had to stop myself from, going on a little sort of like few thousand word rant in a meme group about why I think this headline is problematic. Um, Anyways, my tips for sort of media literacy connected to the AMOC, and obviously this is now sort of more my personal view than the objective science that I've been talking to you about. Uh, First of all, something that is really important to remember is that the Gulf Stream is not going to collapse. The Gulf Stream is obviously, you've probably all heard of it. That's why the media always talks about the Gulf Stream, because it's sort of more easier to understand for people than the AMOC. I don't really even blame them, but like you now going away from this lecture, you will know that the Gulf Stream is not going to collapse. It's a small part of the larger AMOC, so it is part of this whole current circulation, but it's something that basically just happens. If you have a basin on a rotating Earth, you're going to have a Gulf Stream. And even if the AMOC collapses, the Gulf Stream isn't going to collapse. So that will stay there. My other sort of tip for reading these sort of articles is that I would always check the source, because sometimes journalists write articles about preprints, and I would always take those articles with sort of an even bigger pinch of salt, because preprints haven't sort of been checked by anyone. And obviously, if it's just about the AMOC, nothing's going to happen. But we all know that during the COVID pandemic, a lot of misinformation was spread because people would just immediately jump and talk about preprints when a lot of the time they had a lot of issues with them. That's not a fault of anyone there. It's just because that's how the scientific process works. You have to go through, you have someone to like check your paper before you start sort of like making conclusions. I would also personally, when you're reading articles about climate science, I wouldn't trust exact numbers, because climate always comes with uncertainties. So if you see the AMOC is going to collapse by 2050, that's probably just there to be a little bit of clickbait. I mean, there might be numbers in the studies, but first of all, it's just one study. Another study could give completely different numbers. And also, like, climate science usually isn't sort of like good enough to give you exact numbers. There's things that we're very certain about. I'm not like saying here, I'm not doing any sort of climate denial here, of course. Like, we're very certain that like the planet has been warming and that it's caused by anthropogenic emissions. And we can definitely say something like the AMOC will weaken in the future. But if someone tells you the AMOC will collapse in 2050, I'd be a bit more cautious about an exact number like that. Um, Another sort of just personal tip is that I usually like to scroll to the bottom because that's usually where they keep the quotes and reactions from other scientists. And it's always sort of good to read context from like how is the community reacting to this paper. And of course, remember if you're getting very scared about these articles, not that climate change isn't scary, but journalists only write about the exciting, scary articles. So um, yeah, there's a lot of articles out there, and what you're reading might just be, one article out of 50, and they sort of chose the most scariest one to write about. So that was basically my presentation. As a recap for what we've talked about, um, the AMOC is a climate system, a current system, sorry, in the Atlantic Ocean that transports heat and salt northwards. So these warm surface currents going north, sinking down, and deep water, cold water coming south. Um, as we've seen, a collapse of the AMOC would cause like basically cooling of the whole northern hemisphere, some regions more than others, and monsoon rainfall would basically change in a detrimental way over most of the globe, as well as sort of other changes like in carbon uptake or sea level. And we suspect we have good evidence for the fact that the AMOC has an alternative weak stable state. And we suspect that past a certain warming of the planet, the AMOC could collapse to that state. And possibly that collapse could be irreversible, or as I like to say, practically irreversible, because there's no way we could bring the AMOC back. And my take-home messages are a bit similar to the conclusions, but I want to sort of like say again that the AMOC will definitely weaken in the future. No one's sort of like debating that. But what we're worried about is that if emissions continue to be high, it could collapse to a weaker state in a way that like can't be brought back to a strong AMOC. And we need a strong AMOC to keep the sort of stable climate that we have today. But we're not sure when this collapse could happen, and we'll probably never be able to predict exactly which year and when. And sort of my final message, people always sort of ask at the end, and I'm also very happy to answer questions, but people always ask, okay, but what should I do personally about the AMOC as part of climate change? And my personal opinion is that it's really good to know about the AMOC because it's a very important part of the climate, but I don't think there's anything you personally need to change about your climate actions because of the AMOC. It's part of the bigger climate problem, and climate change is going to be catastrophic. Even if the AMOC doesn't collapse, even if we weren't worried about the AMOC collapse, we would still need to be worried about climate change. So the message is always the same, right? We've known what to do for decades. We need to reduce emissions as fast as possible. That hasn't changed. And for the AMOC, there are no local solutions or anything like that. For the solution for the AMOC is the same as it is generally for climate change. Stopping the warming at some manageable level, like 1.5 degrees or 2 degrees or something like that, as soon as possible. And the reason that we study the AMOC is not so much because we think there can be some sort of special mitigation for the AMOC or something, but because we're also interested, in adaptation of like sort of knowing what is coming basically is important. So yeah, thank you for listening. Um, and I open to questions. I don't remember if, yes, okay. I'm sorry, I can't really hear you if that's spoken to me. Um,
Vielleicht noch so nach vorne kommen.
oh, now it's okay. Maybe if you try.
Ich glaube, du musst das vorne vielleicht sogar sagen.
Okay, I hope it's better now.
Yes, yes, yes.
Okay, perfect. Um, okay, we still have some time for questions now. Just a quick reminder, this lecture is being recorded. So if you do not want your voice to be recorded, just let us know beforehand. Okay, we just need some time to carry around the mic. Ah, super.
Mhm.
Wenn du ins Bild reinkommst, bist du aber auf der Aufnahme drauf. Bis dann.
Yeah, I've got two questions. First of all, why is weaker AMOC, or why does weaker AMOC leads to less salt in the North Atlantic?
Yeah, thank you for the question. I'll try to go back to like a figure that maybe helps with this. Um, sorry, just going back to the map of, yeah, the salt. As you can see here, the equator is salty and the Southern Atlantic is saltier, right? So this region here, because of different things like ice melt and sort of river runoff precipitation, it's and obviously evaporation. It's warmer around the equator. There's a lot more water evaporating, so it's saltier. And so these currents that go from the equator up to the north, they're taking saltier water with them up to the north. And so that's why the AMOC is transporting heat and salt. That's what we always say in the Atlantic. And if it gets colder, if it gets weaker, the AMOC, then there's less salt going from the equator up north.
Okay,
Yeah.
thanks a lot. And secondly, couldn't it be a treatment to put more salt into the water, especially there where ice melts to compensate the less salty water?
Maybe I'm not an expert in geoengineering uh like that. Obviously, theoretically, if you were like to do a little experiment in a climate model where you just put a little bit more salt, to me that sounds like it could work. But I can also imagine that with geoengineering, things like that, the amounts of salt would have to be enormous. Like the strength of the AMOC, just to sort of like, talk about the strength of this circulation, we're talking about millions of cubic meters of water moving from one place to another. So this is also the amount of sinking that you're happening. I don't know if this amount of salt would be practical at all, what it would do to the ecosystems, what it would do to the weather. So obviously it's very interconnected, everything that's happening there.
Okay, thanks a lot.
Okay, perfect. Thank you. Are there any more questions in the room? Okay, otherwise there are a few on Zoom. Someone asked, in science, tipping points are highly controversial. How certain can we be that the AMAC could undergo an irreversible change? Is there a percentage probability for this? How does it compare to other tipping points, such as the melting of Greenland's ice?
So yeah, I mean, I agree that they're quite controversial. I think the controversy is more about whether or not we should be focusing on them. Everyone probably agrees that they're like a possibility. They've obviously happened in the past. I think, whether or not we should be focusing on them so much, whether or not we should call them tipping points, that's always a question. I mean, so it was a question about could the AMOC, obviously I've shown you some evidence about the why the AMOC might be a tipping point, but and like I've shown here in this preprint, now we have quite strong evidence that with future warming the AMOC is going to basically go down to zero if we don't do anything. So with the high emission scenarios, the question of whether this is tipping and whether it's irreversible, that's still very much open. And you can't give something like that a percentage because there's very complex questions here, right? Because it's difficult. What we have is both sort of like historical data and simple models, which don't tell us that much. And then we have these sort of complex models, which are sort of biased towards stability. So we can't say that what we see in them is exactly what is happening in the real world. And there's no real way to sort of give a percentage when you just have like a bunch of models showing different things. Yes, the IPCC report said that before 2100, the collapse is unlikely. I think this is definitely like that. Afterwards, we still need to do more research on this sort of very recent results. We need to do more research on sort of like other things about the AMOC. But yeah, I agree that it's uncertain and that we need to keep researching it. My opinion about the controversy around tipping points is that all this research is useful in other ways, right? You're researching the AMOC and understanding different things about it, even if you're thinking about it as a tipping point or you're thinking about it just as a system that might weaken. So yeah.
Thank you. If there are no more in the room, we still have some on Zoom. Yep, doesn't look like it. Someone asked, how does the AMOC influence the climate in Europe, particularly in Germany? What would change if the AMOC reached its tipping point?
Yeah, so this is a figure from an older IPCC report, so it's a few years old, but they did this sort of analysis where like what would happen if the AMOC really weakens, and you can see this has more results in terms of like impacts on humans. I would say a lot of this is sort of quite uncertain because we're only really starting to do this sort of AMOC impact simulations and the models disagree with each other. But what's definitely going to happen is that it will get cooler. Obviously, if you combine this with also the whole temperature getting warmer, it would just be a little bit less of warming. But you can see that also it says that around the Mediterranean, you'd have like sea level rise and less agriculture and food production. But in the context of like climate change as a whole, this might get more complicated and it's still being studied.
Thank you. We still have some questions from Zoom. How could the global economy be affected by weakening or collapse of the AMOC?
That's definitely something that is also still being studied. I think that's why tipping points are actually quite a new field, and the economists have only recently sort of like tried looking at it. I know that, in sort of the very sort of basic economical models, if you just look at temperature, they usually see the AMOC collapse as a good thing because it gets colder, so it like stops the sort of warming. But obviously, if you look at the more complex effects, and I think my supervisor is actually collaborating with some economists which are looking at this, it would be a lot more complicated. So the combination of maybe also drier sort of weather, not just less warming, but also dryness and maybe more storms or something like that, still very much open to research.
Okay, maybe one last question. What would be the effect of an AMOC collapse on marine life and biodiversity?
Obviously, this is not my area of study, but I know that it would be huge, right? Because these ocean currents are very important to carrying around nutrients, carrying around even just the temperature. So if you look at the sort of temperature change, precipitation change, right? This sort of huge cooling in the north and warming in the south, that could have a huge influence, and all the sort of carbon uptake. Yes, it would definitely not be good to change the whole circulation in an ocean basin for the ecosystem in it.
Okay, thank you very much. If there are no more questions in the room, I think that's it for today. Thank you again for your lecture. It was really interesting. And to everyone else, we will see each other next week.
Thank you.